Hello, my name is Andini Zermanasitian. I'm a PhD student from the University of Southampton in the UK. I'm from Maritime Engineering Group. Today I will present the latest work about the sweep angle in propulsive flapping as seen in swimming animals. So this work is based on collaboration with my two supervisors, Bharat Ganapati Subramani and Gabriel Weymouth from the same university. There are so many things that we can learn from the way animals move underwater. They are more flexible for changing directions, they are more adaptable to the environmental changes such as current and waves, and they are also more efficient than any robot that we can make today. So this study can benefit researchers in bioengineering and underwater robotics that also have interest in biolocomotion. The main sources for animals to move underwater are their propulsors, known as the tail for the fishes, flukes for dolphins and whales, and flippers for turtles and penguins. So before we proceed further, I am going to introduce two main terminologies we are going to use today, the sweep angle and the aspect ratio. So you might have heard the term swept wing or delta wing aircraft, so they are similar. Sweep angle, or here lambda, is the angle between the line perpendicular to motion direction number one and the line connecting the front quarter chord of the propulsor cross section, or number two. While aspect ratio is simply the ratio of perpendicular span length square, or b square here, to the planform area of the propulsors. So a report was published for marine mammals data in red dots here for sweep angle versus aspect ratio that look inversely proportional like delta wing. But once I added more data from other animals or from other publications, the spread of the data are getting wider, so it is hard to define the trend of the data. We need a better explanation from a fluid dynamic perspective. For this reason, we study the sweep angle influence in flapping foil by running 3D Navier-Stokes simulation for the sweep angle 20, 30, and 40 degree. So we call it first set here. So the first set is for aspect ratio 4. Then we decided to also run the simulation for aspect ratio 2 and 8. The reason was that we thought the different aspect ratios might affect the influence of the sweep angle. For one set of study, we vary sweep angle while keeping other parameters constant. We simulate half tail or half flipper, and we fix the other parameters constant, such as the static parameter here. For example, the aspect ratio, half B, and chord length C, which is parallel to the inflow or U infinity, so that we keep the Reynolds number constant for each cross section, and also the NACA 16 profile constant. For dynamic parameters, we keep the Struhal number constant. Struhal number is simply the reduced frequency times the specific amplitude. So reduced frequency related to the fact that tail or flipper move at certain frequency, while the specific amplitude defines how wide the foil moves. So for tail, we fix the pitching amplitude, and for flipper, we keep the rolling amplitude constant. Please pay attention to the parameter called L star in here. So L star for tail and for flippers are different. So L star for tail is the one that is parallel to the inflow, while it is perpendicular to the inflow for flipper. I'm showing you now the tail simulation for 20-degree on the top at the top and the 40-degree one at the bottom. Although the vortices, they look different, the propulsive characteristics are very much similar. For example, the LEV breakdown and the TH at the same time, which is every half period, and at the same location, which is the half of L star. And if we look at the coefficients of lift, the forces data here for 20, 30, and 40 degree of sweep angle, the average and the range of the CL are pretty much constant. Similarly, if we look at the flipper simulation in longer aspect ratio, so these are for aspect ratio 8. So before for tail, it was for aspect ratio 4. The timing and the location of the vortex breakdown was still similar at half a period, but now it's at 1/3 of the L star from the tip. And the forces are now is even more similar than the tail. We run extensively about 11 sets or 39 simulation, and we compile together the data using parallel axis or parallel coordinate graph. I will explain about this graph in detail. So the first four axes are the input parameters, while the last four axes are for the output parameters. So the input parameters are the motion, specific amplitude, aspect ratio, and the sweep angle. And for output, we have the average of coefficients of thrust and the RMS of coefficients of lift. So this is the fluctuation of lift coefficient, basically. Mean coefficients of power and the efficiency. For the first input is the motion. We divide into two big categories, which for flippers, which is in blue. Here is rolling for single motion and the combination motion between twist and roll. And for the tails, the single motion is heaving and pitching. And for the combination motion, we have pitch heave. So tails are in red and flipper are in blue. The darker the color showing us, the here they are for a high sweep angle. So for the second input, these are the specific amplitude. So it defines how wide the flapping in comparison with the L star. As we maintain the same Struhal number, high amplitude must be accompanied by low frequency, while low amplitude must be accompanied by higher frequency. So animals tend to prefer high amplitude, low frequency, while most robots we find today, they prefer low amplitude, high frequency. So the rest of the two input are sweep and aspect ratio. We have discussed this. I have an interactive graph version of this graph to isolate more parameter easily. The link will be given at the last of this presentation. If we now highlight the highest thrust coefficients here, low amplitude and high frequency parameter belongs to the robot that actually imitate tails, can produce very high lift and high thrust, but the efficiency are very low because the power are very high. If you notice that the output lines after the sweep angle axis, which is the mean thrust until the efficiency, the lines regroup to their set of 20, 30, and 40 degrees. So this means that the variation of the sweep angles are very low. So if we want now to see the most efficient motion, they belong to the combination motion for both tails and flippers. Only at high amplitude and low frequency motion, which is preferred by animals. We can see again that the lines regroup to every three colors here, showing that actually the sweep variation is not that much. And if we see the single motion, they are very difficult to produce high efficiency. Now, if we are looking at the cross correlation with heat map graph I'm showing you here, the rest of the correlation we use are the Pearson correlations, while for the motion, because they're category, we use the correlation ratio. The principles are the same. The darker the color, the higher the correlation. And for this graph, we can see that both sweep angle and aspect ratio correlation to the output are in pretty much light color, which means that the correlation is very low. We can now draw a conclusion that as the following. So there's no advantage of having sweptback angle for tail and flippers, but that also means that actually there is no significant disadvantage for having sweptback angle. From a biological perspective, the fastest fish from Scromidae family, such as tuna and mackerels, or mammals from the Phonidae family, such as dolphins and orcas, can have a very high variety of sweep angle at any given aspect ratio without actually losing their thrust and efficiency. So generally in flapping foil, the kinematic parameters are more important than the geometry itself. And we have seen that combination motion are more efficient than the single motion. And as we've said before, the animals are more efficient than robots. Thank you very much. So this work is now peer-reviewed in a journal. So anyone wants to read, we also put the draft in bioRxiv preprint. And the interactive graph can be accessed in my GitHub page with the link provided. Thank you very much.